Goedemorgen. Ja, het gaat weer los. Ja, alles gewoon. Ja. Kijk, we zijn aan het uitzenden, we zijn aan het opnemen, alles. Nou, dan moet dit wel even weghalen, ja. Oh, en dan moet ik eigenlijk ook gewoon mijn...
Er zijn wel mensen bij.
Ja,
Nee, dat is
het is wel een beetje een dodelijke tijd, hè? Ook nog op vrijdag, ja. Dus iedereen staat gewoon op donderdagavond in de Paradiso, natuurlijk.
Precies.
As you do, as you do. Ja, oei, oei, oei. Even kijken. De chat, die ga ik er ook maar even bij pakken. Wat gebeurt hier nou, jongens? Ja, uitgemikt. Hello. Oh, I just showed the wrong thing here. It's not the right one. This one is. I have so many presentations running. Ooh, ah. Oh. Good morning. Yeah, we're gonna take some time to, warm up a bit. Yes. Yeah. Where are you getting it?
No idea where is it, like in the beginning.
Me neither. I think it kind of depends on where you want to go, because like there, if you go fully downstairs, then I think there's a line around this one. So that would take more time. But there's also like a little coffee bar that you can get, like the bag coffee.
Yeah, that's fine, that's fine.
Yeah, I think you go and take the stairs up, and then there's a coffee place.
That's the one down. In the corner next to the theater.
Yeah.
Where you also going up the.
Yeah, well, they come off the escalator.
Yeah. It's on the right there.
Right, so you can go up or down, depending on what you want to exit yourself before getting coffee or after. I like might well be.
Yeah.
This building is kind of labyrinthine, is the word.
Yeah, every floor looks the same, but it's not.
Yeah.
Yeah.
Yeah, 9 o'clock is not the best time in the world.
Morning.
But I'm sure we will live. I don't know why that just happened. It's kind of weird. Here we are again. I'm still sharing that screen, it seems. Good morning. I saw you all have been reading already. I saw people asking questions on Perusall. That was really inspiring. I'll talk about it a bit more in a bit. Yeah, I'll wait another 5 minutes before I start talking. Do you enjoy reading the paper? You haven't?
No, I haven't.
That's good. You still have time, I think. So there are a few, this is all a bit like, I'll just colloquially talk a bit about this. So there's a few questions that arose. One was about intuitive reasoning, how that would come about, right? One of the speakers at the CCN conference in 2018, Josh Tenenbaum, talked a bit about intuitive reasoning and how that type of functionality is not really present in present day AI. And there's a lot of interest in this type of thing. So what I've done is, so this was already the plan, but one of the final readings, so we'll do most of the Perusall reading this month. And so at the end of the month, we'll be reading a paper by Josh Tenenbaum. And then there's also a YouTube video where he explains this paper, right? So the two go hand in hand. You watch the YouTube video and you read the paper. Watch the YouTube video first. And that really goes into this whole idea of intuitive AI. There's a few links with different things in the different podcast episodes also, right? So there's links with how, for example, children learn to, think about the world. That there's a certain intuitive reasoning that they have in terms of agents and in terms of the roles that different objects play, that sort of thing, that they learn really naturally. And it's very interesting to go into that. So there's a few podcasts if you're interested, like Liz Spelke has a podcast on this specific subject. I think Alison Gopnik is also an episode. If you're interested in that sort of thing, then yeah, dive right in if that's your topic of interest. The second thing, that there was a bit of confusion, well, maybe confusion is a big word here, but about what a generative model is. And I talked yesterday, no, not yesterday, time flies, but not that fast. I talked on Tuesday about this difference between process models and more sort of data models, right? So you're modeling either the data or you're modeling the process. And so a generative model you can see as a process model. What that means is that you have a model that generates data, right? So you have a mechanism that you've implemented that can generate data. So that's one interpretation of what a generative model means. There's also a more strict sort of statistical sense for a generative model, and that is if your model actually models an entire sort of probability distribution, then the generative model samples from this probability distribution. So it generates samples from a probability distribution. So those are like different ways of thinking about what a generative model is, and we'll be going into this different types of models. Good morning. I mean, yeah, on and on, right? And I'll so whenever this type of concept sort of rears its head in the reading for a given week, I'll try to spend some time just talking about, you know, what the different implications are, where the questions are, and so forth and so forth. Okay. Cool. So let's slowly make our way towards today's lecture. So we'll see how far we get. You can all hear me online, I hope. I'll try to speak clearly. Excellent. So like I said, this course is, we try to have this evolution in the course where we start out with very basic models of behavior, so simple behavioral outputs. And then what I'm trying to do there is I'm trying to show you how even the simplest of data, such as just whether people say yes or no, right? So very, very simple data, how using a model to understand the underlying mechanism can help. Yeah. And so today I'll be showing you a bunch of examples of this type of model that we can use to understand simple behavior. There are many, many more. Every neuroscience field has its own set of models. But I've chosen to really stick to the basics. And what that means is that many of you will already likely know what I'll be talking about. So the exercise for you then, if you're like, okay, I sort of already know this, it's really bachelor level material, you might think. The goal here is the exercise for you as a student is to understand how like using the model actually helps you take a new perspective on what the behavior is doing, right? And we'll show a few examples of that here. We're starting with the simplest possible case, which is signal detection theory. So if you have any questions online, if you want me to go slowly or fast, just raise your hand and I'll try to see, because I see you like as a set of people on the screen here. Cool. So signal detection theory. It is a model. So so it's a theory, it is also just really a model in the way that we want to introduce you to in this course. It's a simple mechanistic model that we can use to explain patterns of data. And the type of data that we're interested in explaining in this case is really the simplest possible experiment. It's choice data. What does choice data mean? Well, you can think of the different types of choices that you encounter in everyday life. And there are many different ones. So have I seen you before? Like it's a facial recognition and memory task. Yeah. It's a real life example of a choice that you need to make when guiding your behavior. And similarly, you want to know maybe if you're on your bike and you're going through traffic, you need to be able to make the distinction or the choice, was that a car honking in the distance, right? And if you're passing by a restaurant, you might want to know, is that the smell of cardamom I'm smelling? So these are all very simple choices that you can make as an observer. Oh, okay. So the sound tends to be not so good. So I'll try this thing again and hope that it won't deafen me or you. Can anyone say something?
Hello.
Yeah, I sort of hear you. It's hard to see. Let me try to check. Well, it works, I hope. And can you hear me online? Okay, let's see if this works. Okay, so that's life. In principle, many decisions and choices that we make they depend on these binary decisions, right? Where you can add, where the answer can be yes or no, right? Very simple type of decision. And some people would argue that you know, really all of life's decisions end up in the end, if you zoom in close enough, they are this choice of something is yes or no, or left or right. Yeah? You either do it or you don't, sort of thing. Okay? So what I'm going to do, so these are examples of yes/no experiments or choices. And if you boil this down into a very, very simple experiment, we call this type of experiment a yes/no. And so this stands for the detection in the signal detection theory words. Detection means, is something present or not? Yes or no. Very simple. Yeah? And so to give you an idea of what that type of choice is in terms of the context, in the context of an experiment, I'm going to do an experiment with you. So we're going to do a yes/no experiment. Yeah. And this is really the sort of standard way in which we perform an experiment like this. Very, very simple. Your choice is to detect this image of a pigeon or a dove. A very elegant looking pigeon, so I guess it's a dove. I don't know really what the distinction between the two is. Right, and so on a given trial, what I'll be doing is I'm going to show you both noise and the dove. Yeah. And I'm going to titrate how much noise I'm showing. So what that means is if I'm going to show a lot of noise, very strong noise, then it will make it harder for you to see the pattern of that dove. That's the idea. Yeah. And so what we're going to do is run a few trials of an experiment. And you should say yes or no when I show an image. And I'm going to start out easy and it's going to get harder. I promise. So this is trial number 1. Yes? No?
Yes.
Good, because if you'd said no here, that would have been problematic. So indeed, yes, this is the answer. There is this dove there, right? And the easy part here is we know exactly what we're looking for. I just showed you, right? And that's really also the that's really clear in this type of experiment. You know exactly what the signal in this case looks like. The signal being the image of the dove. Okay, so next trial. No, right? You could sometimes, and that's the tricky part, right? If you look at a pattern like this noise pattern, you can sort of see things in it, right? And that can be problematic in an experiment like this. So indeed, you all said no, right? And you're very correct. This is no. So you now have had these two different types of choices, right? One in which you clearly saw the pattern and one in which there clearly wasn't. So let's move on and make it a bit more difficult, right? What's your answer here? Yeah. Yes, indeed. So what you've seen is that I'm dialing up the noise, right? And I'm lowering the magnitude of the signal, making them closer together, right? And making the distinction already somewhat harder, but nonetheless, very clear. We are, as human beings, also like very, very good pattern recognizers. So this isn't really much of an experiment to speak of otherwise. So what's this? No? No. Okay. Well, you're right. I've made this also a very simple experiment in that you first get a signal trial and then a noise trial and then a signal trial and then a noise trial. I forget whether I'm really diverting from that pattern at some point. So indeed, yes, no, we just see high frequency noise or high amplitude noise. Here, you see I'm toning it down further, right? So what's your answer here? I already gave it away with what I said, but okay. So you see that we're getting closer and closer to making it hard to see this pattern, right? So indeed, you were all correct, and indeed, this is yes. So wait. So what's this? I double clicked.
Yes.
Can you? Yeah, you know the answer, right? But you're starting to see that it becomes really, really hard to actually discern this pattern, right? If I didn't have a tremor in my hand, some of you might have been fooled and thought this is just noise, right? But indeed, there is a picture here in the background. So the correct answer is no. But what about this one? Or yes, I mean, for the previous one. What about this one? No? Are you sure? Yes. Again, correct. You are very, very astute observers, all of you. Yeah, so again, this is just noise. Let's continue. Yes, you also see the transition, right? So it becomes a bit easier. You're very good at picking that up. Definitely, yes. Let's see when this experiment ends because it's getting a bit. So what about this one? Oh, we're starting to have inter-observer variability here. So you see, now is when this gets really, really difficult, right? It becomes difficult to say whether this pattern is still there. And indeed, this pattern is there. I actually made it, but you know, the contrast is dialed far down so far that you're very close to just flipping a coin, right? You don't really have that much sensory evidence to work with. And that's the thing I want you to experience here. But there is not that much sensory evidence to work with for your brain. And that means that you will start to make errors. Yeah. So we tend to describe this experiment, this extremely simple yes-no experiment with this signal detection theory. The power, so the rest of this sort of part of the lecture, I will really try to explain to you why using this model, this theory, allows us to understand what's going on better than what we could understand if we didn't have the model, right? So you can ask yourself, how good are you at this, right? When do you start making errors? And you can express that in terms of your percentage correct for a given level of the stimulus, if you will. Yeah. And you could say, yeah, I'm like 70% correct. Yeah. So that accuracy actually feels like it should be. Sorry, I have to just move this window because I can't see the next slide in any of these. So you could express this as like, I'm 70% correct, right? And that might be good or not, depending on the context, but at least you have a number, right? And that's a measurement. That number is a measurement, and you could feel all good about yourself, having done science. We have a number. We can start doing statistics on a number, right? So what's important here is that we always need to think about the numbers that we're using, right? We can't just use some number and then start doing statistics on it. We need to really try to understand where these numbers come from, right? So this number accuracy would come from your tally of how many doves you saw over a collection of trials, right? And then it turns out, so this is just how many doves just relates to that percentage that I just spoke about, right? And it turns out that that doesn't really answer your questions if you're interested in the mechanisms behind this. So how good are you at this? The answer to that, as in terms of percentage correct, in terms of accuracy, really isn't a good reflection. So this question of solving the question of how good are you at this using just accuracy doesn't give you the answer. And I'll highlight the problem, and using the model, I can explain how we can go beyond it. So the problem with a yes-no experiment is that people have biases, right? And these aren't just political biases, and that can be a bit confusing because the words do map onto political concepts, right? But in the case of a yes-no experiment, you can be conservative in that you are more likely to say no, right? So we have this discrepancy here. One person said yes and the other person said no, right, with the same evidence. And there we see this difference between different observers. One person may sort of inherently be more likely to say no, and the other might inherently be more likely to say yes. Yes. And so this yes person would be more liberal, and the no person would be more conservative. Yeah? But you can imagine that this being conservative or being liberal might have an effect on your accuracy also, right? Depending on an interaction with the stimuli that you're showing. So if you're very conservative, you end up saying no, 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 no all the time. We're not actually doing a measurement of how good you're seeing. You get that, right? And if you're saying yes all the time, also, it's the bias that we're sampling and not the process that does the perceptual discrimination or the perceptual detection. And so this is very, very problematic But if we just look at percentage correct, which would be like 50-50 at chance, if you're just saying yes or just saying no, we need something more than this. Yeah, so that percentage, that measurement of percentage correct, that accuracy measurement, that doesn't cut it for us, and we need to have a more formal description of this decision-making process. So you see the crux here, right? You see the problem that we might be confronted with. And so in an experiment like this, you have, usually what you do is you have half of the trials where you only show noise, right? And the other half of the trials where you show noise plus signal, the way that I did it, right? So similar to that last couple of trials where you're trying to exert yourself and you sometimes make a mistake. Now, what I'm showing you here in this diagram is the possible set of responses and inputs that are in this type of experiment, just from principles. Yeah. So if you are a noisy observer, sometimes you will say yes, and sometimes you will say no, right? And we have, as experimenters, two types of trials. The first is where we actually show the stimulus that people are supposed to detect, and the other type of trial is where the signal is absent, right? So that's this two columns of this matrix here, where signal is present or absent. Yeah. So that's given by the experimenter, of course. Then we're going to read out the response of the subject by just seeing what button they press on a keyboard, for example. Now, in the case of a signal present trial, you have two response options, right? You can be correct, in which case you hit the presented signal, right? So we call that a hit. Or you miss it, for example, if it's very difficult, right? Sometimes you do mistake the signal for noise, and then it's a miss, right? So the signal was there, but you missed the detection of it. And conversely, on the other column where we don't present any signal on a given trial, you can correctly say that it is not present, which is at the bottom here, the correct rejection. You're accurate, or you're correct. Or you can maybe say yes, and that creates a false alarm. Those are very interesting types of trials, of course, because people are actually saying that they saw something, but there was nothing there, right? So in a sort of basic sense, you could consider this a sort of pseudo hallucination sort of trial, right? They are very, very interesting. But this is the full sort of response matrix that we have for a very simple experiment like this. How many of you know this? Yeah? You've seen this already? You're like, okay, great. So this is generally, I hope we get to go a bit more deeply into why we need a model for this and how this sort of pans out. People use this a lot in other contexts too. Here I'm going to really go into how we're going to use the simplest model possible and to try to explain these responses and try to gauge the underlying processes. Yeah? So with this signal detection theory, I'm going to introduce this underlying concept that makes the reasoning about this process explicit, and we're going to do so in terms of probability distributions. It's all going to be very, very simple. We're going to use the equal variance signal detection theory model. And it's going to be simple in that we model our evidence, so that is the sensory evidence that comes in, as coming from two probability distributions that we propose, that our model posits are just normal distributions, right? And as you may know from statistics, normal distributions have all these nice properties that make them very easy to work with. And they are reasonable to assume because any process that is sufficiently complex will give you probability distributions that are normal. So what we have here is a set of axes, right? So on the y-axis is probability, because this is a probability distribution, that's standard. And on the x-axis, we measure the value of an internal response. So in this case, in the experiment that you just performed, this is doveness, yeah? The likeness to a dove or something, the thing that we're trying to detect. Yeah? So this is the distribution of the internal signal. It follows these probability distributions. If the signal is just noise, is on the left, right? Or when there is a dove on the right. Yeah. So remember that we showed we had these final trials. They're really, really difficult, right? And some of you said yes, and some of you said no. And what that means is that the trials were sufficiently hard. That is to say, I moved for the signal distribution, or when there was a dove, I moved it from all the way here when we started, right? It was very, very clear. And I started moving it further and further towards the noise distribution until such point that they were very, very close together. It became really, really hard to see whether the dove was present or not. And these probability distributions for the noise trials and the dove trials started to overlap. So when these overlap is when you start making errors, because a single measure of the internal response could have come from one or the other distribution. Yeah, that's the key issue here. If you measure, let's say, the value 12 here, that means that that value could have arisen from a noise trial and equally likely from a signal trial. Yeah? And you have no other option but to guess. So you see there's an inherent sort of statistical issue there, and that's the reason why we use these probability distributions. Yeah? Now, the second ingredient for this model is that when we make a decision, we compare the value that we measure on each trial, right? So that is just a single measurement in this model. So we, over like 1,000 trials, these values would have these different distributions. On every trial, we just take a single sample. Now that single sample, we compare to a value that we call the criterion response. Now, if that value that we sample from our sensory apparatus is lower than our criterion, we say this is noise, so we say no. And if this value that we sample is higher than our criterion response, we say yes. Yeah, so we do a very, very simple comparison between the incoming value, that is just a single continuous number, and some internal criterion that we set. And then if you have, so in the top here, we have trials in which there is there was actually a stimulus, right? So the values would come from that right distribution. Now, if you sample from this right distribution, and this is your criterion, you would say yes whenever that sample is to the right, right? And that would give you a hit because we showed a stimulus and you answered yes. Yeah. But it's a wide probability distribution. So sometimes that sample from your sensory apparatus has a value lower than the criterion that you're maintaining. So what that means is that we did show a stimulus, but you failed to say that it was there and you produced a miss. Yeah. The stimulus was there, you said no, you fail. Yeah.
Why is the criterion response like shifting to the left instead of being in the middle?
Ah, yes, that is a very good question, and I'll get just right to that in the next slide. Yeah, so this is all just about the fact that you have a criterion. It's at some value, right? And on any trial, we compare the incoming sensory value to that internal criterion value. Yeah. But indeed, it can be anywhere. And that's going to be the point for the next slide. It's also always the best questions are when you can say, I'll get to that in 2 minutes. Yeah. You had a question too?
No, I just the hybrid response,
Ah, okay, yeah.
which is basically it tells you how liberal conservative.
Oh, yes.
The point of view.
Yeah. Yeah. So what you do with this, and I'll get to that in a bit, but what you do, excellent point, when you change this criterion, which is under your control in principle, when you change it all the way here, you'll be saying yes all the time, right? So you're a very liberal person all of a sudden. You shift it all the way there, you're saying no all the time, right? So you become a very conservative person. That's the idea there. Yeah. But I'll try to explain that in more detail in a bit. Yeah. So you can also have trials in which you're just sampling noise, right? And that was this distribution. Yeah, it's shifted a bit to the left, but it's the same shape distribution. And you are, because you don't know as an observer whether the experimenter is showing you something or just noise, but you have to maintain, you are maintaining the same criterion, right? That's a given. You cannot change that from like omniscient knowledge or something. There's no information for you to change the criterion depending on whether there's a signal or not. You just have this decision process to work with. So you're sampling from this noise distribution, yeah? And luckily it's shifted a bit to the left, which means that much of the probability mass So most of the probability to the left of this criteria is to the left of this criterion. And so you'll be relatively correct, or like in a majority of the trials in which there's just noise, you'll be correct because you'll be saying no here, right? The value falls to the left of your criterion. And so there was no signal, you said no, correct. Excellent, good job. Next trial. On the other hand, for this given criterion, there's also quite a lot of probability mass on the right, which means that for a rather large proportion of trials, this sensory sample that you're taking from, in this case, noise, will give you a value higher than your criterion, meaning you will be saying yes and you are wrong. Yeah. So those are those four categories in the in that matrix, right? But here you see them projected onto the arena of our equivariance signal detection theory model. So it's a different way of thinking about these different categories on this axis of the internal response probability measure. So yeah, what's on the slide now, I just already said this, right? So if your internal response is larger than your criterion, always respond yes, because you don't know which of these two types of trials you are in. Yeah? And if that internal response is smaller than criterion, you respond no. And like we just said, it's your criterion that determines your answers, like the proportion of yes and no, right? And here you see an example of what happens when you change your criterion. And so it's very important to realize, and I'll start hammering on this in a bit, right? What this model does is it allows us a conceptual separation between two different things, namely your observer preference in terms of setting that criterion, right? That becomes separated from this internal sensitivity measure, like the distributions that your sensory apparatus gives you. Yeah? Those are separate. These are fixed. Right? You're changing your criterion does nothing to the underlying statistics of your sensory incoming signals. Yeah? Those probability distributions remain the same. And so what these three situations show you is how changing that criterion, so this is the point relating to your question just now, how changing your criterion will give you different proportions of hits and false alarms. And in all these three cases, you are actually equally sensitive. Yeah? So you'll have different percentage correct values. So the whole structure of what type of answers you're giving changes as a function of changing your criteria. Yeah? If you're very afraid of false alarms, if you're very conservative, if you think that making a yes error is really bad, that's what that is, right? So this is very conservative at the bottom. Then you start saying no a lot, which means you're going to have very few hits, but you're also going to have very few false alarms. Whereas if you're very liberal, you care about not missing the target, then you're going to lower your criterion, thereby saying yes a lot, meaning that you have a very high hit rate, but you will suffer in terms of also having a very high false alarm rate. Yeah? So I'll go into these, like how you balance this as an observer and what the reasoning behind this might be. But first, we'll talk a bit about that sensory sensitivity part of this situation, right? So I just explained to you, we have this part of the model that governs criterion, right? And we just looked at its effects, and now we're going to look separately at this part of the model that has these two probability distributions. Yeah? And it's important to realize that this is really related to the sensitivity of the sensory apparatus. And what I'm saying here is sensory apparatus, that could also be quality of memory, of course. This is just a very sort of standard way of saying it. So, yeah, that's clear, right? You're like I told you before, right? All of these real life situations, they end up being a yes/no discrimination at some point. So this sensitivity can be a memory scale, it can be whatever. So when are you highly sensitive? When are you not so sensitive? Well, you are not so sensitive when these two distributions overlap fully. And that makes sense because regardless of where you put your criterion, the amount of overlap doesn't change, and you're going to have a hard time discriminating between whether something is signal or noise because they just share so much in terms of the probability mix. Yeah? And if you're very sensitive, it means that you have very small overlap. Yeah? And so you are a perfect observer if they are completely apart. Yeah? You're not going to have to make any errors apart from being distracted, for example, during the experiment. Yeah? And so the quantity of interest here, the important quantity here, is how much overlap these two distributions have. And this is also where it becomes very, very important to assume that they have equal variance. So there are different models, more complicated signal detection theory models have different variances that they assume, and that skews everything, makes everything very, very complicated. In this case, what I'm showing you to the left here is two situations in which these noise distribution and the signal distribution, they have different variances, but in effect, they have the same overlap. So the sensitivity is the same. Now, what is the sensitivity? We call that D prime, and that is the effective distance between the noise and the signal distributions. Yeah, so if I scale the width of these distributions and their difference equally, that overlap remains the same, and I have exactly the same sensitivity. So that's what I mean with that effective distance. It's the amount of overlap between the two probability distributions. Yeah. So what's strange, though, is that we're sampling not from these specific distributions, right? So we also always need to take this translation step, right? Our model lives in this probability density sort of space over single trial estimates. But our experiment in the end is what is your hit rate and what is your false alarm rate? The things that I was plotting in the previous slide. Yeah.
You call it effective distance, but it is overlap.
Yeah, it's the same thing. Yeah.
Okay.
Yeah.
Understood.
So so effective distance is like yeah, in terms, so the distance insofar as that it relates to your ability to discriminate between the two, right?
Yeah.
And that ability to discriminate depends not just on the distance between the peaks of the two distributions, but also really on the overlap between the two, right? So, and if you then scale the difference between the peaks equally to the variances, then you still have the same overlap. Now we have these measurements of these hit rates and false alarm rates, right? They're here somewhere, right? And we know how much probability mass fell below and above, right? We know our criterion bisects each of these distributions at a certain point. So what we can do, and if we assume just normal distributions, we can do this C transformation, which just gives us a measure of where am I on each of these normal distributions. And they're normal, so you can normalize everything to have equal variance and variance 1. And so you do a simple transformation, which you call a z-score, and that allows you to calculate this D prime. And so this z-scoring effectively scales back these distributions, and we'll have a look at this in the practical. Yeah, so for many of you, this will be completely elementary. That's fine. For some of you, this may be new, and then that's also fine. I mean, then you've learned something, I hope. In the practical, what we're going to do is really simulate these things, simulate experiments where people perform a detection experiment and do data analysis on these simulations to show exactly how these patterns work and how an experiment like this works. And we're going to go even farther a bit in the practical. What we're interested in is this really weird thing that you have control over your response rates, right? Your hit rate and your false alarm rate, how you distribute your responses in that matrix. But your sensitivity is fixed, right? You won't miraculously be better at discriminating something. You're usually just fixed with your eyesight or with your quality of memory. Yeah? And so what that means is that if you assume that these are the same, and if you use this model, what you can do is you can trace what we call the ROC curve, which stands for receiving operator characteristics. And what it does is it relates this false alarm rate to a given hit rate. And if you are very good, or if your memory is very good, if you're very sensitive, then what you will do is you will sample along this line. So there is a relation between the hit rate and the false alarm rate in this model that allows you to construct these ROC curves. If you're very, very sensitive, you will trace this line, and if you are not sensitive at all, if your D prime is 0, which means that these two distributions are fully overlapping, then you have that straight line. And I'll go into what this curve means. Oh, I just said all this. And so, what is a curve like this? Let's look at that D prime of 2 curve. Okay. So we see it trace this sort of parabolic type shape. And there's for a given false alarm rate, we get a specific hit rate. Now, what does this curve mean? Well, if we're working with this fixed sensitivity of D prime is 2, the curve means that we can change our criterion on top of this sensory situation, and we will trace this curve. Right? So if we are extremely conservative, right, we say no, 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 no all the time. Yeah, it means you'll have 0 false alarms, right? Because you'll never say yes if there is no stimulus. So what that means, you're at 0 here, and the false alarm rate. But of course, you're saying no all the time, so you're never hitting the target whenever it appears either, right? So you're in there. Yeah. And so when you change your criterion, what you're going to do is start saying yes more and more from that highly conservative situation. Yeah? You're going to say yes more and more. And what you have here is that if for D prime is 2, if you do a minor change in your false alarm rate, if you incur a minor change in your false alarm rate, you actually gain a lot in terms of your hit rate. And that is because that noise distribution is so far removed from that signal distribution. And so in the practical, we'll go through this. You'll trace this curve and be able to understand more deeply how this curve comes about. And so what's really important here is that, and I've alluded to this before, right? This model has these 2 stages. One is the signal processing part, right? The sensory sensitivity, as I've called it. And the other is this sort of behaviorally relevant parameter, namely the criterion, right? And so in this case, what you see is that your behavior changes drastically, right? But your underlying sensitivity does not. Okay? So what this model gives us is a way to separate these 2 different ways of thinking about it. Right, so as we change criterion, we can move over this line, and all we are doing is just changing our propensity to say yes or no. So we're shifting that criterion along those 2 distributions. Now, an important insight here is that when I introduced this idea of accuracy, we didn't have this model yet. That was just how correct are you? Yeah, so what I'm going to do now is plot percentage correct in this same scheme, right? In the same axis, and you'll see that there's a very strong. It provides a very different view on what this does, and that's this. And so if you go through here and you construct curves where people have exactly the same proportion correct, so that the chance that you're correct is identical, that gives you these straight lines. So this is percentage correct, 80%, 65, and 50. 50 again being just a coin flip, right? You have no information. Yeah? So very clear to realize here that sensitivity that we were talking about before is divorced from accuracy, right? So your sensitivity is fixed when you change criterion. You have these beautiful curve shapes. In this case, these probability correct lines are very, very different from that, right? So sensitivity is divorced from this accuracy measure. And what this also means, is that our criterion, so that is that bias that we might have to say yes or no, gets in the way of getting the optimal result. Yeah? So I just want to show you that relation between percent correct D prime and criterion by overlaying the 2, right? So when you're sort of stuck with a certain D prime, right? You don't have better memory than you have. And so when you get the best percentage correct, well, the best percentage correct is when you move to the left top. That's when you get better performance. And so, because that's this 50, 65, 80%. Right? So when do you get the best percentage correct? Given some d prime, well, that's when your d prime curve intersects this cross diagonal. Yeah, that's when you're at that, at the most top left in this, along your d prime curve. Yeah. And the point where that happens is the point where your criterion is 0. So when you are an unbiased observer, that is when you maximize your accuracy. I hope that's clear from this overlay. So just to highlight, we'll have a break. Then after that, I'll talk about an extension to this that is more, that accords with real life better. And we'll also go into the practical. So the idea of the practical really is to give you this sort of playground in which you can sort of go back and forth between these different things and really understand what might happen when you perform an experiment. That you always need to be aware of whether you're changing really sensitivity, the thing that you might be interested in, or criterion, right? So this is also where the worlds of sort of engineering or sort of physics that have to do with your sensory apparatus intersect with the world of psychology, which has to do with setting that criterion and that sort of thing, right? So in the next lecture, I'll be talking about how decision making this type of decision is not as simple as this model assumes. It's much more complicated, but it's more elaborate in time. We have the need to respond, and we need to learn and adapt our behavior from our interactions with the world. So I'll get into that after the break. Excellent. And you guys online, you can still hear me? Oops. This is confusing. Great. Thanks, Wesley. So the first part is a recap anyway. So just to recap that SET thing, right? So we have this idea of the mechanisms underpinning our decisions being samples from either just noise or signal distribution. And we have this sensitivity aspect to this, which is that overlap between the two distributions. And we have this decision criterion, which is the inherent sample value above we say yes. Yeah? So that's this type of thing. Situation 1 is where you have a d prime of 0. And in situation 3, you see that we can move the criterion around. So yeah, you can think of that line as that line is conservative. So you can use that line to be more liberal or conservative. Yeah. Okay, but this is the simplest possible model, right? You haven't missed anything. This SDT model is really the simplest that you can do. It disregards many, many different things. And this is also what we spoke about in that previous lecture, right? Building a good model means leaving out many, many different things that might be very important in real life, but that are not part of the thing that you're trying to explain at this moment. Yeah. So this signal detection theory model is a very, very simple model, and it leaves out all of these very interesting things. It does so by assuming that you're just taking a single instantaneous sample of that decision variable. I'm starting to call that sensory sample value, the doveness value. I'm now going to call it a decision variable from now on. That's because we're moving towards a different field, and this is the nomenclature of this field. Now, this instantaneous sample thing, that's not how things work in everyday life. Yeah? In general, in everyday life, time is not, so your life is not based on trials, right? I mean, my life is not, I hope yours isn't either, because that would be boring. Real life extends over time, right? And often you're confronted with a sensory situation where you might actually benefit from taking more time, right? We do this in everyday life by, you just spot something in the corner of your eye and then you look at it and then just, look at it for longer. So you increase your exposure to the sensory evidence. So instead of doing that, right, that thing, I can show it to you for longer, and all of a sudden, you see that you had much more access to the actual information there. Did you see it, or do I need to roll back? Great, yeah. And so what you just experienced, this unitary flash versus the ability to look at that image for longer, something happened in your brain, right? In the first instance, you didn't see it, in the other, you did, I hope. And so that difference, I think, is well, it's not. I think that difference is what we're going to be discussing today, like in this lecture, right? Because we'll be talking about evidence integration, the integration of evidence over time. And this framework really flows very naturally from the signal detection theory, as in you have these sort of random samples, but they are coming from different probability distributions. This field of evidence integration, of evidence accumulation, if you will, is huge. So I'm going to give you a broad overview of the different concepts. But there are hundreds of neuroscientists working in this field with lots of different models. I will highlight the core concepts and show you a few examples of the different types of models. And in the paper that you'll be reading on Perusall, it's written by one of the proponents of one of the simpler types of models. But it does explain all of the necessary concepts very well. Yeah. So this evidence integration. The idea is, whenever we have prolonged access to information, it serves us well to integrate it. Right? If we want to behave optimally, then integrating that evidence is what we need to do. And so we can then try to extend our simple signal detection theory model by saying, okay, we're not just sampling once from that distribution, but we're going to sample multiple samples, right? And we need to find a way to integrate those samples and then use that accumulated information over the multiple samples. So we're going to use the fact that we can draw these subsequent samples. Now, you can imagine that you have like your evidence. So we already talked about like probability distributions, right? So you can think of this sort of thing being, in this case, they're two-dimensional, but that's not really important here. You see that in one case, this drift, this randomly drawing samples, leads somewhere, in the other, it doesn't. And this is the type of thing that we use to model this sort of behavior. The idea is that if there is signal, and I'll show you that graphically in a bit, but if there is signal, you have the signal distribution that's apart from the noise distribution. If you're only sampling noise, you're going to more or less stay in place. And if you're sampling signal, there's going to be a drift in your accumulation of that signal that you're drawing. And then at some point, we're going to say, now that drift has gone to a specific location. So for example, in the blue case, all the way to the left. And then we're going to say, okay, now I know, right? So I need this matter of certainty to make my decision. And this translates, of course, very, very intuitively into this idea that if you have very little evidence on each sample, this drift will be slower. So you have a little, like smaller values that you're integrating. It means that a harder decision will take longer. So you need to integrate more if you have fewer, like little evidence on every sample. And so this is beautiful in terms of how it actually extends from signal detection theory, right? It links this processing of information to action, right? You are actually deciding as an observer, you can be deciding whether you want to sample more information or not, right? So there's really like an action component inherent in this type of extension to signal detection theory. These concepts of drift and that sort of thing may feel a bit vague now, but I'm going to go into that now. But you see that what we have is a core model, signal detection theory, and now we're going to extend it into one specific direction. And we're going to be very clear and very explicit about what we are adding to this model. And in this case, it is time and this sequential sampling. So in sequential sampling, so this is like the larger family of models, we call them sequential sampling models. We have two response options. And I'm going to go back and forth between this sort of yes, no, or a discrimination experiment, which would be like, is that car moving to the left or to the right, right? But we can think of those two things in this basic explanation as the same thing. Namely, we have one distribution of signals standing for one response option. So that's pressing this button, and the other for pressing the other button. And so what we have here is exactly our signal detection theory situation, right? If we take a single sample, we just have to say, okay, what's my criterion? And then I'll make my answer depending on whether the sample is above or below a criterion. But now we're going to do something else. What we're going to do is we're going to add time. Yeah, what we're going to do is sample values from these distributions sequentially. Then, so we're going to add them up cumulatively over time, and that's how we sort of implement time in this model. Right? So it has a very, very clear relation to signal detection theory. Right? We do need to change one thing, and that is this aspect of being able to wait in order to respond. Yeah. Because you're not sampling a single, the time at which you respond is not the same always, right? Because you can sample for longer or you can sample for shorter periods of time. Yeah? And so what we need is a threshold level. We're going to say if my accumulation process hits this level, that's when I answer. Right? Or if my, like for example, that's when I answer yes, there's a drift upwards over time. Okay? Or at the bottom, I'm going to, when my drift hits this level, this threshold, I'm going to say no, for example. Yeah. So what does that look like? Well, we would have this drift, right? We're sampling from these two distributions over time. We're adding them up, right? And you can do this in many different ways, but this is just to illustrate the point, right? And you see that there is signal in this trial, and there is a slow drift towards that threshold value, right? Now, when that drift, so this is a model process, right? We don't know whether this thing that drifts actually exists in the brain. This is just posited by saying, we're just going to integrate information, right? That's it. And then that sort of leads to this idea of there being a sort of object that drifts. Okay? But it's an abstract quantity. So what we get here is a response, which where so here the person that responds would say yes, or it would say right. That response would be yes or right. And we have time. Our measurement now has an extra dimension. It has response time. Yeah. So it's actually much richer already in terms of the things that you get from your data. And this is also something that happens a lot in this field. People use this extra modality of information, this extra dimension that you get from an experiment like this, time, response time, really as a very powerful option. Okay. So here's another trial that might occur, in which case there is more or less nothing on the screen, for example, and it's clearer. Right? The drift is a bit faster in this specific instance. So you have a faster reaction time, and now your answer is left or no. So whenever that dot hits the hits that bound, you are going to respond. So what you're doing, what your behavior is based on is really this thing that drifts. Now, we're talking about this decision variable. I won't quiz you on this type of equation. It will become very clear when you go through the practical. We've also implemented this all in a practical. The idea here is, though, that you have some drift. Right? So that is
or that is related to D prime, for example, right? How far are these distributions apart? That will give you the strength of the drift in some direction, and it can be noisy.
But this sort of spans an arena in which we can start thinking about this, right? So the way that we had our data earlier, our yes/no outputs, and had this probability, this equal variance signal detection theory, it gave us a space in which to think about the process happening, right? And now we have a similar type of arena. Now we can start to simulate this type of behavior, and in the practical we will. So one of the so this is what I just showed you. Really is the most global way of thinking about this type of process, right? You have samples from these evidence distributions, and you integrate them. And in this case, that was just done by summing them. But there are many different flavors of this type of model. And what I'll do is I'll go from the more basic ones to the more elaborate ones, and just show you how you add these different aspects to these models from the more basic ones, and those allow you to model more complicated types of behavior, for example, or like model the intricacies of your data. So one important thing to point out here is that in this type of model, you can actually model the complete reaction time distribution. Right? So we have, if we can implement this in the computer really easily, that means that we can simulate entire experiments within seconds. And what that means is that you can create these whole reaction time distributions. You can simulate reaction time distributions and compare them to what your observers are producing. Your experiment is producing in real life observers. Yeah. And so we get a lot more information than just this yes/no, hit rate, false alarm rate type quantifications, because these are extremely rich descriptions of what's going on. Yeah? So in the paper that you'll be reading, you'll be talking, the author talks about sort of specific shifts in terms of error reaction times and correct reaction times. So you have all of this information to work with to better understand what type of process you are working with. Yeah. And so similar, so so this whole what I've talked to you, what I've said up until now was more about sensitivity, but there's also something similar to criterion here. What we can do is we can shift not just criterion, which would be more or less where you start. That would be one way of manipulating criterion. If you start closer to the upper bound, you're more likely to hit that, right? So that would shift your shift towards yes, responding yes. But the really cool thing is, in this type of model, you can change actually the level at which you say yes or no. And that gives you a dial with which you can manipulate what we call the speed accuracy trade-off. Yeah? You can imagine that if you place them very close to the starting value, then you're going to respond really fast, right? Because that drift is going to hit those thresholds really fast. Yeah? The problem is your decisions are going to be shit, right? Because you haven't taken the time to actually integrate. And this is a universal trade-off. If you take more time, you become more accurate, right? And so what you have here is a model parameter, a model quantity, namely how far these thresholds are away from the starting point, that gives you a way of seeing what someone's speed accuracy trade-off setting is as an observer. So you see that there are a few different parameters in this model. It's where you start, you can have a bias in it. You can sort of tilt the evidence accumulation a bit. We call it drift criterion. So different models implement this type of process differently, but they all have this same idea. Namely, you have like something that you could refer to as a drifting particle. And it's drifting somewhere like you would have, like if you have a charged droplet of oil that has a charge to it and you put it between electrically charged plates, it will also drift, right? That's the same type of process. Has all sorts of physical connotations, like we can do experiments in physics that behave very similarly to this type of machinery. And it turns out that this is a really powerful metaphor for thinking about how the brain makes decisions too. Okay. So I hope this sort of gives you an idea of the
arena that we're in now, right? We've taken that signal detection theory as a sort of basic ingredient. And now we've added time, and it gives us this whole arena to play with. And so in the practical, we'll be going into this a bit and give you a way to simulate these different types of things where you can actually control the speed accuracy trade-off. You can actually start to inspect if you change the speed accuracy trade-off or the drift rate, things like that. What does that do to the reaction time distributions for both correct and error trials? So that sort of thing we can start to model. So we have here really a toy system based on very, very simple principles that can already deliver pretty complicated results. And that's pretty powerful. So if you think of this, well, the thing that I've just shown you is just integration, sort of infinite integration, right? You get a new sample from your sensory apparatus, you just add it to the previous, to your cumulative samples, and then that's it. It's infinite, it doesn't decay that level, and so forth and so forth. There's also, it's not being pulled back or anything like that. There are more complicated models in which people do implement this type of machinery, and one of them was created by a Dutch physicist called Ornstein, which is a German name, but apparently we Dutch still take credit for that then. He implemented a model very, very similar to what I just showed you, but there the accumulation can accelerate or decelerate. So there's an extra parameter there that can accelerate the drift, right? We first had only the A here, and now we have some lambda x, which means that depending on the value of x, so if x is larger or smaller, this can, if lambda is greater than 0, it will blow up, right? So instead of having this nice slow drift towards the threshold, it will do like, so like, you know, like you saw in the coronavirus things, it will become an exponential process. Like mathematically, this gives you an exponential process that will go to the threshold, or it can dampen it also with an exponential process, right? So this is just to give you one idea of how, with this framework, we can add ingredients that make this sort of process more realistic. And we just have these parameters that implement this. So again, we just have a simple model, and we can do all sorts of things. We really have a playground that the model gives us. So I've now spoken a bit about how that works as a model, right? I've talked about how this framework gives us an arena in which to think about this this type of process. But I've always just said, okay, but yeah, we're thinking of this as an abstract quantity, right? This is not something that we think necessarily happens in the brain. Okay? But of course, people being people, scientists being scientists, if we have a model, we're going to use that. You know, this course is also called Neural Models of Cognitive Processes. If we have a model, we're going to try to apply it to the brain. Right? So if we have something, a model that can actually capture behavior, then it isn't such a weird step to think, okay, but if we have this model that describes behavior, let's see if we can find its signatures in the brain. And that is also one of those fundamental things that we try to do when we have a neural model of a cognitive process. We can try to find the signatures of our model's behavior in the brain. It gives us a way of understanding what the brain might be doing. So I'm going to show you two examples of how this type of evidence integration process that you'll also be reading about more this week, how that might happen in the brain. And the couple of slides I have for that are really dense, so I'm going to take my sweet time talking about them. If you have any questions, if anything is unclear, just let me know immediately. Okay? So we have this idea of evidence integration. Now it's important to realize that when you think about this, okay, then we still have our sensory apparatus, right? It gave us these samples, yeah, the momentary samples, if you will, the instantaneous samples. They came from just looking at a stimulus for longer, for example. Yeah. So we still have an incoming sensory apparatus the way that we had it for signal detection theory. We took one sample from it in signal detection theory. We're now taking sequential samples from it in this type of sequential sampling model. So that's one component, but we have a second component. If we want to find evidence of this type of behavior, this type of mechanism in the brain, we need to also find that second component, and that second component is, what is it? So we've been talking about how in this model, not only do we have the instantaneous information, but we have something that accumulates it, right? And yes, and specifically, you need to find, so we have these two quantities, right? We have the incoming information on every millisecond, if you will, right? And what happens over time, this is accumulated. What that means is, what your brain needs to do is it needs to store the previous value of its accumulation process, right? Yes, exactly. This is beautiful, right? Because you extend over time, like you say, you get a memory component in there. You need to remember what your previous states of the sensory apparatus were, if you will. Yeah? And so we have this thing in our model that is that thing that drifts, right? It stands for a memory of previous stimulation. And it's the thing that our model bases its behavior on, right? If that hits a bound, that's when we commit to a response, if you will. Yeah? So here we have our ingredients, right? We still have that instantaneous process. We haven't closed our eyes, but we now have time in there, and that means this memory component, this accumulated value that the brain needs to store somewhere if it implements this mechanism. Yeah. So people have done this experiment since the 1990s, 2000s or something. So many of this type of work is done with single unit electrophysiology, which means that people train a monkey to perform some task and then lower single electrodes into a specific brain region. And what they do is they play the nerve, so you measure voltages on the electrode. And what they do is you pass it through an amplifier and you listen to it. And so as your electrode lowers down into the brain very, very slowly, you will start hearing action potentials being fired. And when that gets loud enough, it means that you're very close with your electrode tip to a single neuron. And so that's why we call this single unit electrophysiology. It's very laborious work. People always say if you get one unit per 2 days of work, then you're in heaven, right? That's when you're on a roll. But just imagine just sitting in the dark with doing that. It's like incredibly boring work. And then you're training a monkey. Even before you start doing your electrophysiology experiment, you train a monkey. It takes months, even years, to train a monkey to do really anything, because they just want to, I don't know, eat bananas or something. And in this case, what they did is they trained these monkeys on a very simple sensory decision-making task. So it's very, very similar to anything that we've been talking about up until now. The idea here is that we have a stimulus that's composed of dots that are placed randomly on a screen, and they move on that screen. And the monkey then has to decide whether that cloud of dots is moving to the left or to the right. So the task for the monkey is to view this stimulus, this pattern of dots, and then at some point make a decision. Now I know it's going to the left. And then if it's going to the left, the monkey makes an eye movement to the left. And if it's going to the right, the monkey makes an eye movement to the right. So it's important to realize that the monkey in this case is not pressing buttons. It's making an eye movement as if it's pressing a button, right? That's what it's making the eye movement for. So the outcome of the decision-making experiment is in this case an eye movement. Yeah. Great. Now this type of experiment is under the experimenter's control in many different ways, but one important way is that you can manipulate the coherence of the motion of the dots. You can see that at the top here. If the motion is 0% coherent, all of the dots are moving in random directions. And if it's 100% coherent, all of the dots are moving in a singular direction. Okay? And you can also do something like half of the dots are moving in random directions, and half of the dots are moving in that singular direction. And you can imagine that with this, you have a dial that's very similar to that doveness thing that I started the signal detection theory lecture with, right? It's very, very simple. So indeed, when you do this sort of thing, if you look at probability correct, and you manipulate this motion strength, of course, when you go towards 100%, the monkey is correct in almost 100% of the cases. And if the motion strength is dialed down, the monkey gets worse and worse and worse. And of course, 50% here is chance level, right? If the monkey had no information, it would be at 50%. Clear? So this is, I mean, you can imagine doing this experiment. I could have set it up easily. So it's like one of the basic experiments of standard sensory psychophysics. Yeah? But now they've managed to do this in a monkey, and you get this, what we call a full psychometric curve. We won't go into that. That's a separate lecture, psychometric curves. Okay. So these researchers, this is, I think, it's a Nature paper, I think this is. It's like really influential. It's been cited over 1,000 times because they really were the first to show this type of evidence accumulation in a brain, right? So that showing that this type of thinking about that a brain must accumulate information and how it does so, that is reflected in actual brain activations. I've sort of given away the clue, but I'll try to work from it. So they are reporting from LIP, which, if you hear it again, it stands for a lateral intraparietal region. So it's the LIP region. It's in the parietal lobe of the brain, which is at the top back of the brain. And there's a sulcus in there, which is called the intraparietal sulcus. It runs in each hemisphere. It runs from the back to the top. And in the lateral bank of that, so that's in the side bank of that region is where this, of that parietal lobe is where this region lives. We know that this region is involved in things like attention, in terms of eye movements, and so forth and so forth. And we also know, this is important for this experiment, that neurons in LIP, they have receptive fields, and I'll go into receptive fields more and more, but they have a portion of the screen that this neuron will fire for if the monkey is going to make an eye movement there. That's why I said that this region is involved in things like attention. You can imagine that when you attend something and you move your eyes to that location also, you need neurons that specify that location, and they are in lateral intraparietal region. Yeah? And so what you get is this: you have a monkey that fixates, then the two targets for its eye movements appear, right? And one of those two targets is in the receptive field of the monkey, of that cell that you're recording from. It's a single unit, you're recording from a single location, from a single cell. And then you show the motion stimulus, and at some point the monkey makes a saccade. Now it's important to realize from this experiment then that the monkey can make a saccade into that neuron that you're recording from, that neuron's receptive field, or out of it, right, in the opposite direction. Yeah? And so what these researchers thought, like what we're doing here is we're looking at a region that's relatively high level. It's very close to the output centers for this decision-making process. Yeah? And we can maybe see what leads up to a decision, and we should see a difference in terms of the decision outcome, right? Because the output is related to what this neuron likes. It's the making the eye movement to that location on the screen, or the opposite. Right? So you should see a huge difference in terms of what the monkey decides to do in the end. So that's gorgeous. So what these people found, and here we have, so this is a complicated slide, so I'll really take my time for it, right? What you have here, it has many different parts. So the first thing is to realize that the color here means motion coherence, and we saw that earlier, right? Motion coherence 0 means that you're at chance because there is no information in the signal. Yeah, 12.5 or 12.8% coherence means it's possible to see it, but it's hard. Yeah, Whereas 51%, I could show you the previous graph, but that's relatively simple. You're at like 90% correct or 80% correct. The monkey is. So we have these different lines in the plot. The dashed lines stand for when the monkey selects to make an eye movement outside of the receptive field that you're recording from. Right? So you don't necessarily expect to see any response, and if any response, you expect to see like a drop in the response, because you know, if these things are spatial, you more likely see it go down than up. And we have these straight lines or non-dashed lines, continuous lines. And then when the monkey makes a saccade into, saccade is the eye movement, right? Into the receptive field that you're recording from. So in principle, knowing that you're recording from an eye movement sensitive neuron, you would already expect a large difference between these two. Because one is making an eye movement into the receptive field and the other is not. But the question then is this just the output center of the brain, or can we find evidence of this model component, this accumulation in this region? Right? That's the question here. Now, one other thing that I've not yet shown you, but that is important here, is that they also recorded I don't think simultaneously, but they also recorded from MT, which is another brain region, which is more akin to this incoming sensory evidence. So this is a motion sensitive region where the firing rate depends on the coherence of the dots. And you see that that is really the case, right? So for the high motion strength, you get stronger responses. But these are more or less static, right? So during the entire time of the monkey looking at the stimulus, they are fixed, right? They just fire at some specific level, and that's it. So we think that MT is looking at the input side of things, right? That signal detection, instantaneous evidence side of this model. That's what we're seeing here. And so now we're going to go into the meat of the issue here, and that is the firing rates of the lateral interparietal regions neurons in the middle here. Yeah? And what you see is that not only are you looking at a response that is there at the moment of the eye movement, which is here to the right, right? So you have the eye movement. All of them are at the same height. Right? So when you're making the eye movement, they're all a very high firing rate versus very low. So you see the outcome happening. But if we then look at it from the start of the motion stimulus that's popping on the screen, right, you see that there is a very large difference in how fast the firing rate rises for the high motion strength relative to the low motion strength and the zero motion strength. That's when you go into the receptive field, right? So when a saccade goes into the receptive field, and the pattern is completely opposite for going out of the receptive field, right? You see this beautiful difference also for the zero. Right? You can see that here the monkey is deciding to make an eye movement into the receptive field, and there's a strong difference between when it's making a decision going in the opposite direction. So the idea here is that what we're looking at is a reflection of this variable that keeps track of past sensory evidence, right? We're looking at a process that accumulates this sensory evidence. So we have a view on the fixed nature of the sensory evidence at the bottom, and we see these mounting curves as evidence of that evidence accumulation. Yeah? So no, it doesn't need to necessarily be incorrect. It just means that it's like, think of this like I'm letting you do the experiment, and I'm letting you press with two fingers, right? And so if I am recording from your right finger neuron, right? Sometimes you're correct and it's going to the left, so you're pressing this button, right? But if I'm recording from this neuron, I will not see anything rising in terms of activation. I will most likely see it go down because I'm looking at the no response, like the option you never selected. That's what you're looking for.
No response.
Yeah. So the neuron in this case is responding to for a saccade that never happens, right? Or it's selective for a saccade that never happens. Yeah. Yeah.
I was wondering if the lines are on average or are just one.
Oh, that's a very good question. Yeah. Yeah, so you can immediately, this is a very good question because you're realizing that on every single trial, all of this is stochastic, right? There's a random element to it, right? And indeed, if you look at the paper, I think they have like 12,000 trials per monkey, right? So yeah, once you've trained the monkey, it's very hard to teach it anything else anymore. So you just keep doing the same experiment more or less. And so this is the average across many, many trials. Yeah. This is also because, well, you can already imagine from the firing rate that you see on the axis here, right? So, hello. Ja.
Ik heb vanmorgen hier gewerkt, die ramen gelopen.
Oh ja.
Ik ben nog vastgelijmd. Zou dit even...
Ja, kijk even rond, joh. Ja, natuurlijk. And so what you see is the firing rate here is around like 30, 40 rate, like 30 spikes per second. So that's like that sort of thing. And you see that it goes up to something like 60. Now, if you're looking at a small enough portion of time, that becomes really like, are you measuring a spike or not, right? Because the inter-spike interval at 30 hertz, like 30 milliseconds, right? So you'd be measuring single spikes on that axis. So a single trial would look like very like barcodey. And that's what you see in this type of literature. People show single trials and it's very barcode-like pattern. And this is just the average across many, many trials. So one very important thing to realize that this is not just something resulting from all of this averaging across different trials, but if you separate everything based on reaction time, right? You expect from that drift diffusion model, from that sequential sampling model, that in a trial where you respond very fast, the stimulus being equal, in a trial where you respond really fast, that drift should have gone really fast to that threshold, right? And the threshold is fixed. Whereas if you have a trial where, you know, for random reasons, the accumulation went really, really slowly, given the same sensory evidence, right? You would expect that to rise very, very slowly, leading to a slow reaction time. So if you separate everything based on reaction time, then you should see this gradient with the fast reaction time trials rising fast and the slow reaction time trials rising slowly. And that's exactly what you see. Yeah? So this again indicates that you're not looking at, you know, like accidentally sampling around the time of the saccade or anything like that. Even way before that eye movement is made, you're looking at something that reflects the accumulation of the evidence, right? So their idea is here that you're looking at this in such a way that you've seen a reflection of that accumulation of signal that we know from the models. Yeah? So this is a very coherent story that we get from the combination of these neuroscientific measurements and this model. We knew what to be looking for, and that really helps us perform exactly the right experiment. Now, here's some behavioral results that are not so very important. So quickly, I will go through a separate experiment that is very, very similar, in which case people did use buttons, left and right hand. And it turns out that when you do MEG, which stands for magnetoencephalography, it's like EEG, but then with magnets. I'm sure someone will explain that at some point. But with MEG, what you have is you have some specificity, so you can definitely look in the brain at different regions that stand for the left and the right hand, for example. Right? So you have a readout very similar to that we had in the thing that we had in the monkeys in the single units. We have across the entire brain. We can read out whether someone is going to press the right button or the left button. Yeah. And we can see if we can find similar things because MEG has a very, very high temporal resolution. So it's not as good as, for example, MRI in terms of spatial resolution, but it has a very, very high temporal resolution. So we can actually look at this integrative process over time. So that's the idea. And I'll go through this relatively quickly because it's all very, very similar to the monkey results, namely that if you look in premotor cortex and M1, you see these signatures in two different frequency bands, right? So you have this oscillatory activity in the brain that you can pick up separately. They did this yes/no experiment, and you can see that you see this rise towards this response time over time that reflects the answer that people are going to give. So you see a different sign signatures because the beta band in general is thought to be like a negative reflection
of the neural processing, and the gamma band is thought to be a positive reflection of the neural processing. But you see this accumulation process in all of these categories, and it relates not to whether a stimulus is present, but it relates to what the subject is pressing. So it relates to that decision again. Yeah. Now, the way that that looks, so again, this is not something that I'll quiz you about because it's very heavy on understanding what exactly is happening in terms of the MEG. But in MEG land, people usually plot the percentage response, so how strong the brain responds, in this case over time, right? Because we have that temporal precision, and frequency, so that those are the frequencies of oscillation that the brain can entertain. And what you see is that when the stimulus is on the screen, you see this, the beta band is around 25 to 30 hertz. You see this blue thing slowly rising as people are making that decision, right? And that is thought to reflect exactly the same type of process as we saw in those single units in the monkeys. So this is really thought to be a pretty general mechanism, this accumulation thing. We've now seen evidence of this in both the single units in these monkeys and across the entire brain in terms of a human decision making, right? So it's not just something in the model, right? In this case, the model wasn't necessarily very, very specifically sort of fit to these data, but the concept came from the model, right? So what do we need to look for in the brain? And the model really helped us single out the types of signatures that we should be looking for in brain activation. Yeah. Again, I think that really beautifully highlights what models can be used for. Yeah. I guess that's it for today. Yeah. I don't have that much to say anymore, I guess. So this evidence accumulation thing, the paper that you're reading now on Perusall is exactly about this. So it goes a bit more deeply into a specific implementation of this type of model, but you'll learn a lot more about how these error reaction time distributions and correct reaction time distributions relate to one another and that sort of thing. Any questions you can pose on Perusall when you're reading that? And all of this will have also a reflection in the first practical. Yeah. Excellent. Then this is it's really shitty that this starts at 9 a.m., but it does mean that at 10:42, your weekend starts, doesn't it? That's just too bad. Yeah. Anyway, have a great weekend nonetheless, and I hope to see you on Tuesday. Yeah.